Okay, let us begin.
Okay.
Welcome to this week's Majorana-Raychaudhuri seminar series. Our first speaker of today is Kepanzi from Beihang University, and he's going to talk about revisiting the fermion-field non-topological solitons.
Okay, thank you. Thanks for the invitation. I'm very happy to share with you my recent research results. The majority of this talk will be mainly based on my recent archive paper. And it will be also related to my recent work in the past several years. Okay, solitons are special solutions of the nonlinear equations of motion. They can be roughly understood as the special localized and long-lived wave packages, which can be stable under the perturbations such as collisions or scatterings. So such kind of solutions exist in many subjects, such as hydrodynamics, optics, nuclear physics, and condensed matter physics. In high-energy physics, we also have many important soliton solutions in quantum field theory. For example, cosmic strings and domain walls, they are classified as topological solitons because their stability is guaranteed by the non-trivial vacuum topology. There is another kind of solitons called non-topological solitons. Their stability has nothing to do with topology. They are stable because they carry the conserved noise charge. Since those charges do not disappear, they can exist for the long time and be solitons. Okay, the non-topological solitons can be further classified into scalar solitons and fermionic solitons. And the latter is the main topic of this talk. The study on fermionic solitons can trace back to the early work in the 1970s and 1980s. T.D. Lee first proved the existence theorems of the fermion-field non-topological solitons, and Edward Wheaton constructed a concrete model to confine the standard model quarks into the solitons, and he called this quark nugget. And the physical picture of this early work can be summarized as follows. The model should contain at least one scalar field phi and a fermion field chi, and they interact with each other via this Yukawa interaction. And the shape of the scalar field is expected to have this non-trivial double vacuum structure, as you can see here. The true vacuum is at W, which is the global minimum, and the false vacuum is at W prime, which is only a local minimum. Suppose if there is some space region occupied by the false vacuum W prime, then it will contract to zero due to the inward vacuum pressure because the universe turns to state at the lowest energy state. However, if this false vacuum region W prime has trapped some fermions inside its interior, as sketched here, then this region will not disappear, because when you are compressing fermions into a smaller and smaller region, they will develop an outward degeneracy pressure. When this pressure is able to balance the inward vacuum pressure, we will have a stable soliton solution here. The fermions are trapped in the false vacuum because of this Yukawa interaction. You can see here, the mass of the fermion is proportional to the vacuum expectation value of the phi field. So outside the soliton, where it is the true vacuum W, the fermions are very massive. But inside the soliton, the phi value is W prime, which is much smaller than W. So the fermions are much less massive inside the soliton. So if the kinetic energy of the fermions is not able to overcome this mass gap, then the fermions cannot penetrate to the true vacuum. They will be trapped in the false vacuum to form solitons. And since this Yukawa interaction is invariant under a U1 phase transformation of the fermion field, we can treat that the one fermion carries one unit of conserved charge. So if you trap the Q fermions in the false vacuum region, equivalently you have trapped Q charges here. So since those charge is conserved, these solitons will not disappear, and it can be long-lived. So that is a fermionic soliton. That is the basic picture. Okay, in the last several decades, people have done a lot of studies on this object, and they have found that these solutions exist in many particle physics model, and the mass, depending on the parameter space and model building, can vary from GeV scale to galactic level. So this very vast mass range has very rich cosmological implications, such as being the dark matter candidate, realizing the baryogenesis, or even sourcing the primordial black holes. Okay, but if you're concerned about the calculation method, the methodology of getting the soliton profile, you find two very representative features. The first one is people usually assume a polynomial potential because that is easy to calculate. The second one is that people usually assume the fermions inside the soliton has a uniform spatial distribution because that is also easy to calculate. In that case, you can even express many equations, such as the degeneracy pressure, as analytical functions of the soliton charge and radius, and then you will have fully analytical results. So that's very easy to derive. Okay, so these two simplified assumptions are fine. However, they cannot deal with more complicated case. For example, if you want to deal with the classically conformal theories, then you have to study this logarithm potential, and it is definitely not a polynomial. On the other hand, if you want to study the soliton formation in the very early universe, you have to take into account the thermal corrections from the hot plasma in the early universe. So in that case, you need to include this finite temperature field series correction, and definitely this is not polynomial. On the other hand, in fact, the fermion distribution inside the soliton is not uniform because of the influence between the fermions inside the soliton and the phi field. Because when you combine a lot of fermions in a small region, they will source an additional scalar field, which will modify the vacuum structure of the original V-phi scalar potential. So in that case, the vacuum structure is modified, and this will in turn impact the fermion mass, and hence in terms impact the fermion distribution. So you will eventually have a non-uniform chi distribution inside the soliton. So the original motivation of my study on this topic is to improve the calculation of the soliton profile, such that we can apply it to general potentials going beyond the polynomial assumption, and to include the influences between the fermions and the phi field to have a more accurate profile. However, after the calculation, I have found that the improvement of methodology brings new insights to the worldview. That means based on the new calculation results, now we have many new understandings on the fermionic solitons, and that is what I'm going to share with you in this talk. I will not go into the calculation details. Okay, so this is the calculation framework. I use the relativistic mean field theory to calculate the profile. In this framework, the scalar field is treated as a classical background field, and the fermions are assumed to be in a parameterized Fermi-Dirac distribution. And in that case, the whole system can be expressed as by two distributions. The first one is the scalar field phi x, and the second one is the Fermi energy epsilon f, defined in this parameterized Fermi-Dirac distribution, as you can see here. And all the thermodynamic observables can be expressed as the functionals of these two functions. For example, the charge, or say the particle number, can be expressed as integral. And the energy, or say the soliton mass, can also be expressed as here. And the same happens to the entropy and free energy. Okay, and a soliton solution is to minimize the free energy under the constraint of Q charge, because as I mentioned before, the definition of the non-topological soliton is to localize some conserved charge in a small space region to have a small ball. That is a soliton solution. Okay, so this mathematical problem can be resolved by the Lagrange multiplier method. That is to define a new functional, which is the free energy functional plus the charge functional minus the localized charge constant and multiplying by this mu parameter. And you have to resolve these three equations to get the soliton solution. Okay, the first equation, the red one, tells us that the Fermi energy should be a constant. Okay, previously we treat this as a space-dependent function. It is general. However, now this equation tells us it should be a constant. That constant is mu. It is the multiplier, and it also has the physical meaning of chemical potential. And the third equation, the blue one, constructs a mu-q mapping. That means in this formalism, mu, the chemical potential, mu is the input parameter. And for a given mu, we can resolve the charge. However, if we put in a charge q, we can also resolve the chemical potential mu. They are conjugate observables. Okay, and the second equation, the green one, is the most important one. It is the master equation of motion in this study. It is a differential equation of the scalar field phi. Resolving this equation, we can get the soliton profile. Because as I just mentioned, we have only two distributions here. One is the Fermi energy epsilon f, and the other is the scalar field phi. Now, the first equation tells us that the Fermi energy is just a constant. Then we have only one distribution left. That is the phi field. Once we have resolved phi field via these equations of motion, then we can get the whole soliton profile. And if you look deep into this equation of motion, you can see that the right-hand side includes not only the bare scalar field V from the Lagrangian, it also includes the contribution from the fermions that are trapped in the soliton. So that is the additional new contribution that included in my framework. So in total, you have to deal with this effective potential, including both the bare potential and the fermion contributions. Okay, if you look into the shape of this fermion contribution, you will see that it has this Weyl-like shape. That means the Yukawa interaction is always attractive, and it promotes the aggregation of the fermions. And this potential plus the bare scale potential in the Lagrangian is the total effective potential we need to deal with to resolve the soliton solution. Okay, if you further assume the soliton is a small ball, is a spherical symmetric, then the Laplace operator here can be replaced by the different derivatives on the radial distance, and then you can get this equation. Okay, this is a secondary second order differential equation, ordinary differential equations. And the right hand side is the effective potential as sketched here. To resolve this equation, you need to include two different boundary conditions. The first one is when R approaches infinity, function approaches the true vacuum value of the bare potential W here. That means when you go outside the soliton to the exterior of the soliton, you should be in the true vacuum of the bare potential. That is the trivial solution. Okay, and there is another boundary condition that when R is 0, the first order derivative of phi should also vanishes. That means that the behavior of the phi distribution at the origin should be fine. It should not have some cusps. It should be smooth. Okay, so such kind of equations of motion plus such kind of boundary conditions can be resolved by a mathematical trick proposed by Sidney Coleman in the 1970s. In this trick, R is treated as the effective time, and phi is treated as the effective position. And these equations of motion can be treated as a massive point moving under the negative effective potential and time-dependent damping force, this term. Okay, and the boundary condition is that the first boundary condition says this massive point is dropped at rest at some point of this potential. It is dropped at rest because the effective velocity is 0. And the secondary boundary condition says that it should asymptotically climbs up the right hilltop at this true vacuum. Okay. And Coleman has argued that if the shape of the negative potential, effective potential is like this, namely it has two hilltops and the left hilltop is higher than the right hilltop, then we always have a soliton solution satisfying this equation and these two boundary conditions. And the argument is as follows. If you drop the massive point at this blue point, then it can never reach the right hilltop because of the damping term, okay? Because if you lose energy due to this damping force. So that is the undershoot case. However, if you drop this massive point very close to this green point to the top of the left hilltop, then if you eventually overshoot the right hilltop, because if you stay initially if you stay very close to the left hilltop for a very long time until the time-dependent damping force decays to almost 0, then it rapidly rolls down, and the mechanical energy conservation tells us that it will eventually overshoot the right hilltop. So since we have the overshoot and undershoot cases, the continuity of the nature tells us there must be some point between these 2 points at which we can have a solution satisfying the boundary conditions and the equations of motion. And that is the soliton solution sketched in the right-hand side here. Okay, so from this argument, we can see that the existence condition for a soliton solution is the negative potential has two hilltops, and the left hilltop is higher than the right hilltop. So equivalently, we can say that the condition is the effective potential has 2 values, and the left value is lower than the right value. This brings us the first new insight to the fermionic soliton. That is, the solitons actually live in the true vacuum of the effective potential rather than the false vacuum of the bare potential. So in the previous studies, for example, in T.D. Lee's or in Edward Wheaton's statements, they always consider the fermions being trapped in the false vacuum of the bare potential. However, in our framework, we have demonstrated that the formation of soliton actually requires the true vacuum of the effective potential, including the fermion contribution. Note that this true vacuum of the effective potential is not the same as the false vacuum of the bare potential, although they can be close to each other, but they are different in principle. Okay, so that is the first new insight. And from this statement, you can also find that the shape of the bare potential is not crucial. It is the effective potential whose shape is crucial in the soliton formation. So it might happen that even though the bare potential itself has only single vacuum, we can still have a double vacuum effective potential via the fermion-induced term, because the fermion term will deform the potential and generate an additional minimum here. So we don't even need a multi-vacuum bare potential. This is different than the previous results. This is the new insight. And from this, we can go to the second new insight of the soliton profile. That is, we can extend the concept of solitons. For example, if we choose the quadratic potential, phi minus W squared as the bare potential, then in that case, we can still have the soliton formation because of the fermion-induced term. Okay, we already argued that. And in that case, if you shift the scalar field by this W, you will see that the Lagrange is equivalent to a model that includes the massive fermions attracting with each other via this long-range Yukawa force. So actually, this kind of object has been studied from an independent pathway by another group of people. They are called in those researches, they are called the fermion bound states. Okay, so that is, we just argue that the bound states are a subset of solitons because they can be treated by our unified framework. Previously, people thought the bound states are totally different from fermionic solitons because in the conventional descriptions, fermion solitons requires non-trivial shape of the Bayer potential, and it traps the fermions in the false vacuum of the Bayer potential. While on the other hand, the conventional bound states need long-range Yukawa to attract the fermions, massive fermions together to form bound states, just as the multi-electron atoms or multi-nuclear nuclei. Okay. However, in this study, we have demonstrated that both of them are kind of are solitons, and the soliton actually live in the true vacuum of the effective potential. We need to take into account the fermion contribution. Okay. To move to the next new insight, I have to talk more about the chemical potential mu. It was the multiplier in our mathematical method, and it can be also treated as the jet mass of a chi particle inside the soliton because of this variation equation. Okay, so if you want the soliton to be stable against the evaporation to the free particles, then you need this jet mass smaller than the free fermion mass outside the soliton. So if mu is smaller than the free fermion mass, that means effectively a fermion is less massive inside the soliton than outside the soliton. Then it would like to stay inside the soliton. So that is the first stability condition. And the second stability condition is against the fission. That means the second order variation of the energy or say mass of the charge should be smaller than 0. Once this is satisfied, then the soliton will not split to two smaller solitons. Okay, this is also called the classical stability. So that means the mu has a maximal value, and if you apply this first stability condition to the second stability condition, you will find the variation of mu on Q is smaller than 0. That means mu decreases with Q. So combine these two conditions, you will see that mu should have a upper limit, and in that case, Q is reach its minimum. So there is a minimal charge to form a fermionic soliton. Below this charge, you will not have stable solitons. Either the solitons evaporate to free particles, or it will split to smaller and smaller solitons and eventually disappear. Okay. And when you decrease the mu parameter, the chemical potential, the Q charge increases. And when mu approaches its minimum, Q approaches infinity. And that is called the saturation limit. And I will shortly talk about that. As you can see here, when you decrease mu to its minimum, eventually the true vacuum of the effective potential will be almost degenerate with the false vacuum here. And then it can be proven that the scalar field distribution is almost uniform inside the soliton. So that is implicitly assumed in the most studies, as I mentioned before. So that means most studies are assuming this saturation limit, which is a kind of a special case in our general formalism. So in that case, we can get the analytical expressions of the energy of the soliton and derive the those profiles, such as mass and radius, as analytical functions of the charge and the vacuum energy of the model. Okay, so now we have reproduced the previous results in the literature. And there is another important analytical limit as follows. When Q is small and the fermions are non-relativistic, in that case, the soliton looks like some heavy fermions bounded by the Yukawa attraction. So this is called a Yukawa attraction limit. In that case, the energy can be decomposed into the kinetic energy of the fermions and the Yukawa attraction energy. And we can also get the analytical results, which is consistent with previous literature. So combining these two important limits, we can see the tendency of the radius as a function of the Q charge. That is the third new insight. So when you keep adding charges into a fermionic soliton, then the radius first decreases and then increases. That is because when Q is small, we are in this Yukawa attraction limit. So when you add more and more fermions, they attract with each other more tightly. So the radius decreases. However, if you add a lot of fermions into the soliton, then eventually we will approach this saturation limit in which the charge and the radius both tend to infinity. However, the number density of a soliton keeps as a constant. That means the radius scales like the charge to 1/3. Okay, this is the assumption made by most literature. However, when Q is small, the saturation analytical formula do not apply. So one needs to be careful in this region. And of course, this new insight is not totally new because it is known in the fermion bound state studies in many years ago. However, now we have obtained it in the general fermionic soliton study. Okay, so the previous discussions assume we already have a soliton. Okay, but next I will talk about the phenomenology. Because can exist does not mean must exist. The actual production of soliton is another non-trivial topic. So independent of the feature of the soliton, which we just talked about in half an hour. Okay. If you really want to produce those solitons in the early universe, typically you need to build some specific models with non-trivial dynamics. For example, the solitons can be formed by the direct fusion from free fermions. As long as you can somehow compress Q fermions into a small region. Sorry, is that a question?
No.
Oh, okay. Okay, so but this process is not easy to happen, of course, if the threshold Q minimum is very large. The probability is highly suppressed. Okay, a more frequently used and popular approach is to trap the fermions via the bubble walls in the early universe. Those walls can either be from the first order phase transitions or domain walls. So as the domain walls contract or the first order phase transition proceeds, those bubble walls can compress the fermions to small regions and eventually form solitons. And during this process, if you have some CP violating interactions between the fermions and the bubble wall, you can even realize baryogenesis because you can only trap the antimatter into the fourth vacuum region and form solitons, and then the normal matter are filtered out to the visible sector, and then you have both the matter-antimatter symmetry and dark matter. That is a very attractive idea. Okay. And the solitons can also be formed via the fragmentation of scalar fields, such as the applied dying field. But this needs will need more numerical simulations. Okay. And next, I will talk more about the first order phase change induced soliton formation because I have done a lot of work here. First order phase transition is the decay of the universe from the false vacuum to the true vacuum. And it can happen in the early universe because the shape of the scalar potential can change with time due to the thermal corrections from the hot plasma. So it might happen in some model that at the beginning, the universe stays at the true vacuum here. However, as the universe expands and cools down, there develops another deeper vacuum here. So the universe will decay from the false vacuum to the true vacuum because a barrier has forbidden the smooth rolling. Okay, so this will cause this continuous jump of the order parameter 5. So this is called a first order phase transition. And it will result in the bubble nucleation and expansion in the universe. This is much like the boiling of the water. So it is called the boiling of the universe. inside the bubble is the true vacuum where the phi field takes the non-zero value W star. And outside the bubble, it is the false vacuum where the phi field takes the zero value. Okay, so during this process, if we have some fermions interacting with bubble wall via this Yukawa interaction, then the mass of the fermions will have a gap inside and outside the bubble wall. So if this mass gap is large enough, then the fermions do not have sufficient energy to penetrate into the true vacuum bubble because their energy is the same order as the phase change temperature. So actually, this can be numerically calculated here. I'm not going to go to the details. You can just check this figure. As you can see here, as long as the mass gap of the fermion is a few tens multiplying the phase change and temperature, the trapping of the fermion, the trapping efficiency is almost 100%. So that means almost 100% of those fermions are trapped in the forced vacuum region. So as the phase change proceeds, they will be compressed into a smaller region and forced to annihilate with their antiparticles, as you can see here, to a pair of the scalar bosons, which eventually to the standard model particles via the Higgs portal coupling. So this is an unfortunate result. That means even though we can trap the fermions via the mass gap in the forced vacuum region, they can still annihilate and disappear via this process. Okay, as you can see here, eventually, even though we can trap the fermions such that the number density of a forced vacuum remnant keeps almost as a constant, but eventually when the fermions are compressed to a very small region and the number density is very high, eventually they disappear via annihilation. This Y is the Yukawa coupling strength here. Okay, so to have something left, to have some non-trivial results, you must have some number density asymmetry between the fermions and the anti-fermions. This can be achieved by either thermal fluctuations or the asymmetric dark matter scenarios. So in the thermal fluctuation scenario, the number density, the number of the excess of the fermion is proportional to this phase change temperature to 3/2 power. Okay, and in the asymmetric dark matter scenario, you can use the leptogenesis-like scenario, use the heavy particle decay to generate a Chi asymmetry, similarly to the baryon asymmetry of the universe. Okay, so in that case, if we assume the saturation limit where we can have analytical estimations for the soliton profile, we can get the charge, mass, or say energy, and radius and abundance of the solitons today using some simple analytical formulas with the phase change parameters as input. Here, alpha is the phase transition strength, which is the latent heat over the radiation energy at transition. And beta over H star is the ratio of the Hubble time to the phase change duration. And the temperature is T star, and the bubble expansion velocity is VW. So once you have those parameters from first order phase transition, you can estimate the profile of the solitons which are formed during this phase transition. As you can see here, in the pre-existing Chi asymmetry scenario, you have one additional parameter, that is the Chi asymmetry Y. Okay, and in the thermal fluctuation scenario, you do not have this free parameter, and you can have those typical profile here, which I will not discuss in detail. You can check the numbers. Okay, but I need to emphasize that those estimations are valid only under the saturation limit, as you can see when the Q is very large. In that case, the phi distribution inside the soliton can be treated as a constant. So in that case, we can have the uniform fermion distribution, and then we have this simple analytical results. But if you are considering some high-scale soliton formation, in that case, because it forms in the very, very early universe, and the horizon contains only very few particles, in that case, the charge of a soliton might be small, and the distribution of the fermions is not uniform, and you cannot use those analytical formulas to estimate the soliton. You have to deal with the full master equations of motion, as I mentioned before. Okay, after the formation, the solitons can have different evolution paths. For example, it can accrete the free chi fermions in the plasma to grow up. This is also called solitosynthesis. This process is active when the free chi fermions in the plasma are abundant. And the solitons may also evaporate to free chi fermions or to other particles via the decaying chi. The first scenario is because as I mentioned before, the formation of the fermionic solitons requires a minimal charge. There is a charge threshold to form solitons, but this threshold depends on the shape of the scalar potential. And in the early universe, the shape of the potential will change with time, with temperature. So it might happen that at formation, the charge is larger than the threshold, so we can have soliton. However, below some temperature, the threshold increases and the charge is smaller than the threshold. And then in that case, the soliton will evaporate to free particles at late time. Okay, and the second scenario is that if the chi is not absolutely stable, if it is slowly decaying, then the soliton can evaporate via the surface to other particles. This can be used to realize the baryogenesis or the decaying dark matter scenario. Okay, the final topic is the collapse to primordial black holes. Previously, many people, including me, thought that the soliton can collapse to the fermionic solitons can collapse to primordial black holes due to this internal Yukawa attraction, just like the gravity-induced collapse of the stars. Okay. However, the concrete calculation via this improved framework has shown that they are not able to collapse via the Yukawa attraction, because the Yukawa is important only when the charge is small and the fermions are non-relativistic, as you can see here in the left side of this figure. In that case, although the Yukawa is important, the solitons are not massive enough to collapse into primordial black holes. If you want the collapse, then you will put a lot of charge into the soliton to make it heavier. But in that case, it will approach this saturation limit where the Yukawa interaction is negligible. So it will not collapse via the Yukawa attraction. So that is the bad news. However, we still have a good news that at the saturation limit, even though the Yukawa is negligible, the ratio of the Schwarzschild radius to the radius of the soliton is still increasing. It scales like the charge of the to the 2/3 power. So collapse can eventually happen if Q is large enough, if the soliton has accreted a lot of particles. So eventually we still have the possibility of collapsing into primordial black holes, but the mechanism is not via the Yukawa attraction. That is the fourth new insight. So finally, I comment on the experimental signals of those solitons. If we do have such small balls today, then we can detect them via the gravitational lensing. And if they are formed in the early universe via frost-solidifying emissions or domain warps, then we can detect those processes via the stochastic gravitational wave background today. And they can also produce astrophysical particle signals today via the collisions of between the solitons and captured by neutron stars and accretions with the normal matter. And those processes typically emit 5 quanta, which can generate emit 5 quanta or results in the high interaction with the standard model particles, which can result in the gamma ray signals or positron-electron currents. Okay, and the direct detection experiments such as Xenon 1-ton or Panda-X can also detect those solitons as long as they are light enough and the number density is large. In fact, the scalar qubits are already constrained by the Xenon 1-ton data, so I expect the fermionic solitons will be probed in the future via those large detection experiments. Okay, so I think time is up and I can come to the closing remarks. In this talk, I introduced a framework to calculate the fermionic soliton profile, including the general, the method to deal with the general non-polynomial potential and to take into account the influence between the trapped fermions and the scalar potential to have a more accurate soliton profile. And the improvement of methodology brings new insights to the worldview. This includes the first one is the soliton actually lives in the true vacuum of the effective potential, not the false vacuum of the bad potential. And second, the fermion bound states are a subset of the fermionic solitons. And third, when you add a charge into the soliton, the radius first decreases and eventually increases, and you can have the saturation limit. However, if the charge is not large enough, you should be careful because the analytical formula from the saturation limit might not apply. And the final new insight, the solitons can collapse to primordial black holes via large charge. They are unlikely to collapse via you cover attraction. Okay, thank you for listening. That's all.
Okay, thank you for the nice talk. Any question from the audience now? Please unmute yourself and ask.
Hi, yes. You discussed the fermion soliton, so is there any lower or upper mass bounds if it's related to first order phase transition? Because I saw that you showed a picture of the trapping in terms of the mass over temperature. So can we estimate some mass information for the fermion? Yes, here. So can we say if we consider first order phase transition with the temperature around say MEV temperature, so the fermion mass also around MEV temperature is favored, right?
Yes, I think we can at least have the lower limit of the fermion mass by this trapping condition. For example, if the phase transition is at MeV scale, so the mass should be at least the tens of MeV or even GeV. Otherwise, it cannot be trapped.
Okay. And thanks. And another question is, when you discuss the equation of motion, the second order equation of motion, and you're using the shooting method. So my question is there any other methods that can solve the equation of motion? Because as far as I can tell, when you use shooting methods, you need to tune some initial conditions, right?
Yes, that is a very good question. Unfortunately, I do not know any other method. So for me, I use mathematics to resolve this equation just by trial and error method. I just try one and tune the next dropping point, and eventually I get the converged solution.
Yes, because this equation motion is also appears in first order phase transition. It's so familiar, and people nowadays seems to use the shooting method. So I'm wondering whether I need methods to calculate to solve these equations.
I don't know either. Yeah, you're right. That this equation is the same as the bounce solution equation in first order phase transition.
Okay, thank you.
Yeah, thank you for this question.
Okay, any other question from the audience? Please unmute yourself and ask. Okay, if not, let's thank the speaker. Thank you for the
so much.
And
okay.
will you be able to send us the slides?
Yeah, of course. I will send you via email.